Good morning. Good morning, it's great to see you. I'm Joanna Murphy. I'm the chair of the National Parent Forum of Scotland and I represent the Glasgow area. Thanks to you all for coming along today to this National Parent Forum of Scotland Back to School session. I'm glad you could join us and I welcome our Science Centre partners for helping us today. I'm especially pleased that we're launching with the Glasgow Science Centre. As a Glasgow parent, I visited the centre so many times with my children and I love going there. This is the first of our many back to school webinars we've arranged. You'll see them all listed on our website and I hope you can join us for some of the others and explore the different science centres across Scotland. We're recording all of the sessions, so if you do miss any or you want to share them with your friends, you'll be able to view them on our YouTube channel. The links will be available after the sessions, or if you haven't signed up already, sign up for our newsletter where they'll be publicised, or you can always get them on our website. As a parent myself, I know how difficult and challenging the last few months have been. The school holidays were very welcome, but probably not like any other holidays you've ever had. So we thought these sessions would be a good way to move us all gently back into learning before getting back to school. I really hope that you and your children enjoy them. Before I hand over to the Science Centre, I'll just go over the housekeeping for today. Everybody will be muted and all cameras will be switched off, so you'll only see and hear from the presenter throughout most of the session. If you have a question, please use the chat function. If it's not possible to answer you during the session, we'll try to get back to you afterwards. And I'm sure you'll all be respectful, but remember that many children are joining with their parents here, so please consider this before posting your comments. There'll be a link. We're not doing any surveys at present, but feel free to go to our website and after this to see and let us know how much you've enjoyed the session. It'd be really helpful if you could do this. Please use to remember to use the hashtag NPFS back to school and share pictures of yourself or your children taking part, because we'd really love to see them, whether it's you're taking part this morning live or even if you're watching back on YouTube. Let us see how interested you are and how much you've enjoyed our sessions. I hope you really have a great time. And now it leaves, without a further ado, I'll hand over to the Glasgow Science Centre and good luck. Have a great morning and we'll look forward to seeing all your pictures after the session. Bye-bye.
Morning, everyone. Thanks, Joanna, for that introduction. My name is Steve Owens. I'm an astronomer at Glasgow Science Centre. I have worked here for a long time. I was one of the first staff members to begin working in the Science Centre when it opened in 2001. And I have left and done other jobs and come back. In fact, this is my third time back at the Science Centre. It is an incredible place to work. Hopefully, some of you have visited before. If you haven't, hopefully what you're about to hear might inspire you to visit in future. We're currently closed, as you can imagine, but we're working on our reopening plan at the moment. So hopefully we'll be able to start communicating that to everyone very soon. So as an astronomer, I'm going to talk a little bit today about how astronomy can be used to inspire pupils, children, adults, everyone really, to get involved and interested in science. It's one of the linchpins of what we deliver here at the Science Centre. We have a spectacular state-of-the-art planetarium that allows you to become immersed in astronomy in a way that you can't do on a computer screen. The only real comparison is being out under the real sky. So today I'm going to talk a little bit about astronomy and how it inspires people into science. But I want to talk about astronomy as well. I want to tell you some amazing facts that we've discovered and the process by which we've discovered these amazing things. So I'm going to switch to my presentation. Here we go. So the first few slides are just text, but don't worry, we'll get onto some pretty pictures and some spectacular science very shortly. And these series of webinars, as John mentioned, are to help you as your children are beginning to think about going back to school, introducing the kind of learning they might undertake when they go back to school. And astronomy is present throughout the curriculum for excellence in Scotland. The topic that astronomy sits in, or rather space as they call it, sits within the planet Earth topic. And at every level, there's astronomy content in the curriculum. So overall, in the Curriculum for Excellence under Space, the learners will develop their understanding of the Earth's position within the universe while developing a sense of time and scale. They develop their understanding of how our knowledge of the universe has changed over time and explore ideas of future space exploration and the likelihood of life beyond Earth. I mean, that's a pretty bold statement. The first sentence, especially, developing a sense of time and scale. I don't know about the children watching or even the adults watching. As an astronomer, and I've been interested in astronomy my entire life, I don't think I've got a full understanding of the sense of time and scale of the universe, but the Curriculum for Excellence hopes to build on that and allow people at least to begin to understand that our planet, the planet we live on, planet Earth, is just one of many planets in the solar system, and our solar system is one of many in our galaxy, and our galaxy is one of many in the universe. And that's a massive understatement. You'll see shortly just how big space is. As Douglas Adams said in The Hitchhiker's Guide to the Galaxy, space is really, really big. So when you begin your school career in the early phase of the curriculum, this is nursery up to primary 1, the experiences and outcomes in the curriculum suggest that pupils will have experienced the wonder of looking at the vastness of the sky and can recognize the sun, the moon, and the stars and link them to daily patterns of life. So this is just beginning exploring astronomy, beginning to understand that indeed we are on a planet. It's quite hard to remember that when you're walking to school, traveling to work, cooking dinner, watching TV, but we are all inhabitants of a planet. Our planet is the same kind of planet as many other planets out there. There's nothing particularly unique about the planet Earth, except, of course, it's got us on it. And because we have evolved intelligence and curiosity, we can ask questions about the universe. As far as we know, there's no other intelligent life, at least that we found in the universe. We'll talk a little bit more about that later. But the curriculum begins by asking people just to look up and appreciate the vastness of the sky and recognize the pattern. So this is a beautiful photograph of a sunrise over Scotland. And again, something that we take for granted, the sun rising and setting, day happening and nighttime happening. These things are natural cycles, and they occur because we inhabit a planet that is spinning. Our planet Earth spins once a day. And as it spins, sometimes we're pointing towards the sun, sometimes pointing away from the sun, giving us day and night. It might sound straightforward, but it's not obvious to especially young children that that is the reason that day and night happens, because our planet spins. Our planet also orbits around the sun. That gives us the seasons. Because our planet is tilted over on its axis, it's spinning around a line that's kind of tilted over about that much, about 23 degrees. And if our axis, the part of the world that we inhabit, the northern hemisphere in Scotland, if that's tipped a little bit towards the sun, then we get summer. If it's tipped away from the sun, we get winter. In the winter, the sun is lower in the sky, the days are shorter, the night's longer, it's colder, and that's because the sun never gets that high up in the sky, doesn't beam its heat and light down on us very directly. Whereas in the summer, theoretically at least, we should get warmer days. The days are certainly longer in Scotland in the summer. Whether they're warmer or not, I'll leave you to judge. It says nothing about the rainfall. And then moving up in the curriculum into first level, so this is junior primary up to kind of primary 4, talks about safely observing and recording the sun and the moon at various times. The pupils will be able to describe the patterns of movement and changes over time and can relate these things to a length of a day, a month, a year. This is expanding what we just talked about. So the first stage, the early stage of the curriculum, is just recognizing that there are patterns, cycles in nature that are governed by astronomy. But as you move up in your school career, you will begin to understand these patterns a little bit more. One of the most obvious patterns in astronomy are the phases of the moon. So if you go out on a clear night, even in Glasgow, most nights you'll be able to find the moon if it's clear. And you'll notice if you go out every single night and kind of sketch the shape of the moon, that the moon appears to change shape. We call this changing phase in astronomy. Sometimes it's full, big round moon, sometimes a tiny little sliver of a crescent, sometimes a half moon, sometimes halfway between half and full, what we call a gibbous moon. And these different phases are because the moon, which is just a big ball of rock orbiting around the Earth, is lit up by the sun, and different at different times of the month, different times in its orbit around the Earth, we see different fractions of that lit surface. So when we're looking at a full moon, we're seeing the entire lit half of the moon. Half the moon is always lit by the sun, and during a full moon, we can see all of it. When you look at the top left-hand image there of the moon, that little crescent, half the moon is still lit there, but we're kind of looking around the edge. We're only seeing a little bit of the lit face of the moon. Now, the moon is an amazing thing to start your astronomy career with. It's a really simple thing to find. If you've got clear skies, the chances are you can find the moon in them somewhere. It's not always visible. Sometimes the moon is what we call a new moon, when the lit face is pointing away from us, and for a few days every month the moon isn't visible to us. But on most nights, chances are you'll see the moon somewhere in the sky. Just looking at it with your eyes is enough. You begin to be able to see that there are brighter and darker patches. You won't see nearly this much detail with your eyes, but if you happen to have a pair of binoculars at home, even just a small pair, that will dramatically enhance your view of the moon. You'll see a spectacular view even through a simple pair of binoculars. And when you look in detail, you can see these darker and brighter patches. Even with the unaided eye, you can see them. And people talk about seeing the man in the moon. I'm never that sure where the man in the moon is meant to be. I think the two big round blobs in the upper right-hand side are meant to be his eyes, perhaps. But I can see the upside-down rabbit on the moon. On the right-hand side, if you look at the full moon there in the bottom left, the right-hand side of the full moon, there's those two big round blobs. And off the bottom blob, there's two, what I see as ears sticking down from the upside-down rabbit. Have a look for yourself next time you see a full moon. If you've got good eyesight, you should see the upside-down rabbit there. If you can see it, the head of the rabbit is a very special place indeed. The head of the rabbit is called the Sea of Tranquility. Now, it was named, as most parts of the moon were, before we knew the moon didn't have water on it. When people first looked at the moon without telescopes and binoculars, they thought these dark patches were oceans or seas. We now know that they are dry, smooth lava beds. There's no liquid water in the moon at all, but the names have still stuck. So that is the Sea of Tranquility. And it's possibly familiar to you because that is the place that people first set foot on the moon. Back in 1969, Neil Armstrong and Buzz Aldrin landed Apollo 11, the Eagle lander, on the shore of the Sea of Tranquility. So you can see it for yourself next time you see the moon looking anywhere near full up in the sky. Moving on in the curriculum, we get to late primary. This is primary 4 up to primary 7. Talks about observing and researching features of our solar system. The pupils can use simple models to communicate their understanding of size, scale, time, and relative motion within it. So this is the first time in the curriculum where pupils are asked to think of the solar system and their place in it beyond the Earth. Up until now, we've been down here on Earth looking up. We see the sunrises and sunsets. We see the phases of the moon. We recognize stars in the night sky are different from planets, perhaps, in the night sky. But this is the first time in the curriculum where we're building a model of what the solar system actually looks like. And our solar system is just a family of planets, moons, asteroids, comets, and other things that orbit around our local star, the sun. So understanding scale in the solar system is pretty tricky. Space is big. Planets are also varying in sizes, some bigger, some smaller. The Earth feels pretty big when we're on it. If you remember the days when we were allowed to travel on holiday, it took quite a long time to get anywhere on the Earth, even just a few hours to get somewhere in Europe. If you want to travel to America, it would take the best part of a day traveling once you got to the airport, and then getting to Australia and the other side of the world took even longer. But the Earth is a relatively small planet in the grand scheme of things. And here is an image of the planets, the 8 planets in our solar system, lined up from left to right, with the sun over on the left-hand side. So the sun is our star, and I suppose the basic difference between stars and planets is that stars shine with their own energy. They generate energy inside them through nuclear fusion, and that makes them beam light and heat and radiation out into space. Planets don't do that as a rule. Planets are smaller than stars. They don't have enough energy inside to generate their own energy internally, and they don't broadcast, they don't shine that light out like stars do. And you can see from this scale image how much bigger the sun is than the planets. The sun is vast. In fact, compared to our planet Earth, the sun is about 1.3 million times bigger. That means you could fit the Earth over 1 million times inside the sun. And remember, the Earth feels pretty big when you're on it, but is relatively small compared to other things up in space. It's small compared to other planets too. Once we get past Mars, so the first 4 planets in order from the Sun, Mercury, Venus, Earth, and Mars, are naturally grouped into a category. We call them the terrestrial planets, the rocky planets, Earth-like. They're all crunchy on the outside. You could land a spaceship on them if you wanted to and wander around. But after you pass Mars, you get into the realm of the gas giant planets, Jupiter, Saturn, Uranus, and Neptune. Now, these gas giant planets are, as the name suggests, made of gas and very big. You can see to scale here how much bigger Jupiter is than the Earth. In fact, Jupiter is the largest planet in the solar system. Its volume is so big that, in fact, you could take all the other planets and fit them inside Jupiter and still have room left over. Now, Jupiter, Saturn, Uranus, and Neptune, unlike the Earth and the rocky planets, don't have a solid surface. They're just made of gas. If you tried to land on any of them, your spacecraft would just vanish into the clouds, never to be seen again. If you could build a strong enough spacecraft to withstand the pressure of the atmosphere, eventually, as you travel through the atmosphere, it would get thicker and thicker. Your spacecraft would begin to get crushed. But if you can get deep enough inside the atmospheres of the gas giants, you might end up traveling through something a bit more like a liquid, and then eventually find something a bit more like a solid, but they aren't rocky, solid planets like the Earth. So this gives you a sense of scale. What this doesn't let you see is the scale of the space between the planets. We've bunched them all up close together here so you can see them in one picture. If you want to represent this properly in terms of scale, this slide would have to be about 100 meters long. So it is very hard to understand scale and the size of things in space. Images like this can begin to help you understand it, but they don't tell the whole picture. Understanding and visualizing the whole picture is something that most of our brains, mine included, can't really cope with, because our brains haven't really evolved for understanding big distances or massive sizes. Our brains have evolved for hunting on the plains of Africa, not for contemplating the cosmos. Here's another image that shows you the relative scale of the Earth compared to our star, the Sun. Our Sun is a very active star. It has explosions on the surface of it all the time. These eruptions sometimes cause what we call solar flares, huge eruptions of hot plasma, hot gas erupting from the Sun. These flares can blast that material out into space. And this is a real photograph of the Sun taken just after a flare has erupted. And you can see that one single flare is bigger than our entire planet. So the Sun is vast and energetic, and our planet is tiny in comparison. Now, don't worry if your brains are starting to hurt by this point. Mine certainly does when I'm trying to understand things of this scale. But this is the point in the curriculum, late primary, where we're beginning to ask the pupils to begin to understand a little bit about how their planet Earth sits within the bigger scheme of things, and how these scales look when you zoom out from our little planet. Let's continue zooming out. This slide here is artist impressions. These aren't real photographs, artist impressions of different stars. So every star you see in the night sky is a sun. Our sun is a star. The only difference is that our sun happens to be much closer to our planet Earth, and therefore it appears bigger in our sky. It gives us daylight. We can feel the heat from it sometimes when it's up in the daytime. Stars at night look different, but that's only because they're much further away. To give you a sense of how much further, it's about 1 million times further from the Earth to the next star as it is from the Earth to the Sun. So our star, the Sun, is much, much closer to us than the distant stars are. And therefore they appear just as tiny little faint specks. They aren't close enough to be very bright and very hot, but they are just suns. Some of them are much bigger than the Sun. And this slide shows some of the very biggest stars we know about. So the two big ones here, Betelgeuse, the left hand of the two large stars there. Betelgeuse is a star in the constellation of Orion the Hunter. Orion is one of the most famous constellations, one of the most famous pictures in the night sky. You can't see it at this time of year in Scotland. You've got to wait until October and November before it begins to appear. But Orion the Hunter has a shoulder. He's a stick figure of a hunter, of a man, and his left shoulder is an orange star, the star Betelgeuse. The other star there, Antares, is the brightest star in the constellation of Scorpius, which is only visible low in the sky in the summer in Scotland. And Betelgeuse and Antares are what we call supergiants. They are very big. Now, I say very big, we can compare them to the Sun. Some of you might have noticed, right in the bottom left-hand corner of this image of stars is a tiny little speck labeled Sol. Sol is the technical name for our star, the Sun. So that tiny little speck, it's about a pixel big on my screen. That's how big our sun is compared to giant stars like Betelgeuse and Antares. And remember, you can fit our planet Earth 1,000,000 times inside that tiny little speck of Sol, which gives you a sense of just how big stars can get. The reason that Betelgeuse and Antares are so big is that they are dying stars. They're running out of fuel, and as they run out of fuel, they're starting to frantically burn other things to keep them active. As they burn these other things, they're expanding. As they expand, they cool down and become this distinct red color. And any day now, Betelgeuse is going to die. It's going to explode in a huge supernova explosion. It will tear the star apart, and it will make that star in Orion, the one you can see on Orion's shoulder, it will make it the brightest thing in the sky apart from the sun and the moon. So bright that it will be visible in the daytime, and it will also cast shadows at night. It will be incredibly bright, much brighter than anything else we can see in the night sky apart from the moon. Now, when I say any day now, you should always be suspicious of astronomers when we say that. For us, that's sometime in the next few million years, which isn't really any day now for normal people, but in astronomical terms, that's what we're dealing with. Sometime in the next few million years, Betelgeuse is going to explode. It might happen tonight, might happen next week, it probably won't, and it probably won't happen in our lifetimes. But one day, relatively soon, in astronomy terms, Betelgeuse is going to go bang. And let's zoom out even further. Let's try and get a bigger sense of scale and perspective on things. This is a photograph taken of a neighboring galaxy. This is the Andromeda Galaxy. Now, we haven't really spoken about galaxies. Galaxies are huge collections of stars. Our galaxy we call the Milky Way. It's the galaxy that the sun exists in. All the stars in the previous slide exist. All the stars you see in the nighttime sky are all inside our galaxy, the Milky Way. The Milky Way is big, space is big, so we can't fly outside our galaxy to take a photo of it. It would just take too long. But luckily, there are other galaxies up there in space that let us look at, understand how our galaxy might appear. So this is the Andromeda Galaxy. It's the closest big one to the Milky Way, and it's roughly what we think our galaxy might look like from the outside. It's a little bit bigger than us, maybe about twice the size of our Milky Way, but in the grand scheme of things, both the Milky Way and Andromeda are pretty big galaxies. What you can see there in the center is a very bright bulge. That's where lots of dense stars are packed. And then coming off that bulge are these beautiful, delicate spiral arms. And those spiral arms are full of stars. There's dust in there too. That dust doesn't sound all that exciting, but it's dust that makes planets eventually when planets begin to form around stars. So we can look at other galaxies and understand a little bit about what our galaxy might look like, and again, understand a sense of scale. If this was our galaxy, our sun is not in the middle. We're not in the central bright bulge of our galaxy. We're about 2/3 of the way out from the center in one of the little spiral arms of the Milky Way. We know that because we can look from the inside out and kind of build a picture of what our galaxy looks like from the inside. And taking a step out even further in scale, this is perhaps one of the most spectacular astronomy images ever taken. It's perhaps not as beautiful as some of the other pictures that you've seen or might see online, but for me, this is just an incredible image. This was taken by the Hubble Space Telescope. It's called the Hubble Ultra Deep Field. And what we wanted to do in this picture was take a photograph of empty space. And we turned the Hubble Space Telescope, probably the best scientific instrument ever built, we turned it on a tiny little speck of sky that didn't have anything in it. And we left the camera open for a long time, took a very long exposure of that tiny part of sky. To give you a sense of how small this part of sky is, this photograph you're seeing here is of a tiny bit of sky that if you took a pound coin and held it at arm's length, the Queen's eye on the pound coin would be bigger than the patch of sky that you're seeing here. So it's a tiny, tiny little speck of empty space. But as you can see, once we got the photograph back, it's not empty. There's stuff in it. And all of this stuff exists in that tiny little speck of sky, smaller than the Queen's eye in a pound coin held at arm's length. And the amazing thing is that every single thing you can see in this picture, every blob and speck of light, is a galaxy. And every one of these galaxies has, on average, 100 billion stars. That's a billion with a B, 100,000 million stars. So space isn't empty. There's galaxies wherever you look. And from this little image, from this tiny little speck of sky, we were able to work out how many galaxies there must be in the whole universe. Because all you do is count how many galaxies are in this picture, work out how many patches that size it would take to cover the whole sky, multiply those numbers together, and you get an estimate for how many galaxies there are. Our current estimate is that the universe contains something like 10 trillion galaxies, each with 100,000 million stars. Now, don't worry if your brains are melting out your ears at this point. Our brains are not designed by evolution to cope with numbers of this scale. If I ask you to close your eyes and picture one red apple, I'm sure you can manage it. 2 red apples, probably. 5 red apples, you might not have a perfect image, photographic image of that. If I asked you to do 10 or 20 red apples, you'd have some kind of abstract idea of what that might look like, but you couldn't visualize that number. Never mind 100,000 million times 10 trillion to work out how many stars there are in the universe. These numbers are big. Let's go back to the curriculum. This is moving into secondary school and into the early part of secondary S1 to S3. And the curriculum asks that using their knowledge of the solar system and basic needs of living things, that pupils can produce a reasoned argument on the likelihood of life existing elsewhere in the universe. This is a tall order because astronomers don't know the likelihood of life. We have reasoned arguments, and this is what the curriculum is asking. And I suppose it's also asking us to, look at all the different things that are required to make life possible in the universe. Let's understand a little bit more about this. Let's start with our planet. Here's our planet Earth. This is a very iconic photograph taken by the Apollo astronauts aboard Apollo 17 in 1972. It's famous, this photograph, known as the blue marble. It's one of the first high-resolution image of our planet taken from this distance to show the entire planet at once. And it's photographs like this that were taken by the Apollo astronauts and have been taken on subsequent space missions that allowed us to understand that our planet is just a living, breathing thing. There's no borders on this map. There's no political boundaries here. Our planet is an entity in space, a lump of rock. The thing that distinguishes our lump of rock from others, though, is that it's covered in water. And all life on Earth requires water. We used to think that it required sunlight too. That's not true. There's life deep in the ocean floor and trenches in the Pacific Ocean that doesn't require energy from the sun. It gets its energy from geothermal currents under the Earth's surface. But the common denominator of all life on Earth is that it requires water to exist. So it's natural that when we're looking for life elsewhere in the solar system or elsewhere in space, we start to look for water. Now, one of the criticisms of that approach is, well, what if the life is not as we know it, Jim? What if it's different kinds of life? What if the life elsewhere evolved not requiring water? That certainly could be possible. But we know that life does happen in the oceans. It evolved, it started in the Earth's oceans. So it's a good place to start looking for water elsewhere in space. Sure, we might find life completely unlike anything we experience here on Earth, but at least we know life on Earth exists and that life requires water. So we look for water elsewhere. One of the places we look for it is our neighbor. This is the red planet Mars. Now, Mars today is a cold, dry desert planet. There's no water on Mars today, but there was in the past. And we know this because we've sent an armada of spacecraft to Mars, orbiting the planet, taking photographs from above, and driving about on the planet from below. And these spacecraft have sent data back to Earth, and that data allows us to conclusively say that Mars used to have water on the surface, probably vast amounts of water. We think oceans worth of water. Now, those oceans disappeared a couple of billion years ago, but they were around while Earth had oceans. Earth's oceans have been here from almost the start of our planet. So at some point in the past, there were 2 ocean worlds in our solar system. Life had already begun in Earth's oceans. Life evolved in Earth's oceans just a few 100 million years after the oceans themselves formed. So maybe life evolved in the Martian oceans too. We don't have any evidence of that yet, but we're looking. Let me show you a few pictures that show why we're so confident that water existed on Mars in the past. Here's a photograph taken by a spacecraft orbiting Mars, looking down from above. What we see here is very symptomatic of what we see on Earth when we look at dried up riverbeds. This is a river delta. You can see flowing from left to right, the flow of liquid. Now, it could be other liquids, but the chances are it's water. We know that there's water on Mars today frozen in ice under the polar caps. Here's a photograph of a crater near one of the poles of Mars, and inside this crater is a huge lump of frozen water ice. So there is the chemical compound water there. It's just too cold at Mars for it to be liquid. But perhaps sometime in the past it was warmer. Maybe Mars had a thicker atmosphere in the past, and that allowed rivers to flow and form riverbeds like the one that we just saw. And then we've got rovers on the surface of Mars that are driving about taking photographs of rocks. Here are two photographs. The one on the left is from Mars, the one on the right is from Earth. And we've seen rocks like the one circled on the left there that look like they've been smoothed and sculpted by flowing water. Rocks that don't have water around them tend to be jagged. Rocks that you find in stream beds or river beds or lake beds are smoothed by the erosion of the water around them. We've also found compounds in the rocks on Mars that can only possibly have formed underwater, in craters that at the very least used to be lakes and possibly were part of larger oceans on Mars. The water on Mars vanished, probably after Mars lost its atmosphere. And if there was life in the oceans, the chances are it's not there today, but who knows? There might be pockets of water, liquid water, still trapped beneath the Martian surface where conditions are right for it to stay liquid. Perhaps life continues in those little pockets of water. We find that on Earth. If you go to Antarctica, there are lakes in Antarctica that are frozen over at the surface, but liquid underneath. And those lakes have been cut off from our ecosystem, from the atmosphere, for hundreds of millions of years, but still there's life in those frozen lakes in Antarctica. So there could still be life on Mars. No evidence yet that there is, but we're beginning to build up this picture. We're sending more spacecraft all the time. In fact, as I speak, there are 3 spacecraft flying through space towards Mars right now, and they'll begin to add more bits of evidence, more pieces of the puzzle of whether Mars ever had life in the past. This image is of one of Saturn's moons, a moon called Enceladus. Enceladus is quite a small moon, but amazingly, Enceladus has liquid water. Beneath this crust, the crust of the moon is ice. Beneath that crust of ice is an entire global saltwater ocean. How do we know? We haven't landed there, we haven't drilled through the ice to look. Well, there are cracks in the surface. You can see them at the top of this picture. These cracks go all the way down to that ocean beneath the surface. And we can see the water erupting in geysers from the surface of Saturn's moon Enceladus. Now, we've got spacecraft. We have had spacecraft around Saturn visiting its moons. And the last spacecraft to go to Saturn, a spacecraft called Cassini, flew through these plumes and detected water, detected salt water. Not only that, detected the signatures of hydrocarbons, the same things you find at the bottom of the ocean on Earth, where life exists. Now, we haven't detected life, that's crucial to say, on Enceladus. But we've got all the building blocks there. We've got saltwater ocean, we've got the building blocks of life. Who knows whether there's life on Enceladus? And that's one of many places we find in our solar system that have got oceans. In fact, at the last count, I believe there are an estimated 10 oceans in our solar system. This is all new. We didn't know this 10 years ago. We thought the Earth was the only place to have liquid water oceans. But now we've got at least one moon of Saturn, if not 2 or 3. Probably a few of Jupiter's moons have got oceans beneath the surface too. Possibly Pluto, very distant from the sun. Even at that distance, there's good evidence that Pluto might have liquid water beneath the surface. And remember, all you need on Earth is liquid water, and eventually you get life. Is it intelligent life? Might it be violent intelligent life like in War of the Worlds? The chances are probably not, so don't panic, as the Hitchhiker's Guide to the Galaxy said. The chances of us finding life in our solar system, personally, I think is quite high. I think we will find it in one of these oceans in the next few decades, but it won't be intelligent life. It will be very primitive, probably very simple life like existed in the Earth's oceans in the early days. But maybe life exists elsewhere. Maybe there are planets around other stars, because after all, space is really big. There are plenty of stars out there, plenty of planets out there. Might intelligent life form in one of those? Well, astronomers have this equation, and don't panic, we're not going to get into too much detail about this equation. This is called the Drake equation that just gives us an ability to estimate how many technologically advanced civilizations there might be in our galaxy. So that number on the left-hand side, N, is the number of Star Trek style or Star Wars style intelligent civilizations in our galaxy. And it's important to say we have no idea what any of these numbers really are, but we can make educated guesses about what these numbers might be. We know that the rate of star formation in our galaxy is a few stars every year. And we know that that second term, the fraction of stars with planets, is really high, probably close to 100% of all stars have got planets. Then you have to start wondering, well, how many planets in each star system have an environment suitable for life? Just a few years ago, we might have thought that number was quite low because the Earth is the only place in our solar system that we knew had an ocean. But we find other oceans out there too. So maybe that number is higher than we thought it might be. Just because you've got an ocean doesn't mean you'll definitely evolve life. What's the fraction of planets which have oceans that will form life? We don't know. And from that, how many of those planets will make intelligent life that can communicate, etc., it's pretty tricky to understand. But we can begin to piece together this puzzle to make an estimate of how many civilizations are out there. Personally speaking, I don't think we'll find intelligent life in our galaxy. It's not to say there isn't life out there. I'm convinced there is. But as well as our brains not really being equipped to deal with big numbers or big distances or huge scales, our brains also aren't very good at dealing with big time. And we've got to ask ourselves, how long does a civilization last for? How long are we going to be here on planet Earth with technology? Now, if I asked you this last year, you might be a bit more optimistic than people perhaps are these days, given that we're experiencing a global pandemic. One of the ways that civilization might be interrupted on a planet is global disease, asteroids falling from space, war, for example. There are lots of things that might eventually make a civilization collapse. It seems impossible to think about that in our current situation, but the Romans thought the same back in the early part of the first millennium, and the Roman civilization collapsed eventually. So how long do civilizations last for? Let's say optimistically, we're going to last 10,000 years with our technology. There could have been 1 million civilizations like ours in our galaxy, each lasting 10,000 years, and not one of them would have overlapped in time with another. So not only do we have to find life as a needle in a haystack in this huge galaxy, we've also got to happen upon it at exactly the right time in its existence that it's got technology to communicate with us. Personally, I think that's quite unlikely, but that's just an opinion. I don't know whether that's true or not. Other astronomers will differ in their opinions. And then as we enter upper secondary, we begin to explore research developments about how we build an understanding about how we know these things about space, about our cosmos. The Pupils research developments using that we use to explore space, they can illustrate their knowledge of how the universe, illustrate how our knowledge of the universe has evolved over time. Back in the early days, when people were first trying to work it out, we thought that the Earth was the center of the universe, surrounded by crystal spheres on which were embedded the planets and the stars. We know that model isn't correct. Contrary to popular belief, people in ancient Greece didn't think the Earth was flat. I was born and raised in Inverness. I just drove up the road to take my son to visit his grandparents last week. And if anyone's driven the A9 recently, it's covered in graffiti suggesting that the Earth is flat. It isn't. The Earth is a ball of rock in space. We've got photos of it. We've got astronauts in orbit around it. The Earth simply is not flat. But you can be forgiven for thinking that it might be if you don't possess the technology or the science to understand that the Earth is a ball of rock orbiting a sun in space. Our understanding of the universe has changed just in the past few hundred years. There's a statue in a square in Rome of Giordano Bruno. He was a monk who was interested in astronomy and suggested in 1600 that the stars in the night sky were suns, each with planets going around them. He was burned at the stake for saying so. We know he was right, but it was a revolutionary idea back then. Galileo, who was one of his compatriots, 10 years after Giordano Bruno was burned, turned a telescope for the first time on the night sky. No one had ever looked at the night sky with a telescope before. They were new inventions. And Galileo saw 4 little specks of light orbiting around Jupiter. This is roughly what he would have seen. Jupiter is the big bright blob, and the 4 specks of light we now know are the moons of Jupiter. Galileo observed them night after night and saw them change position. You can do this for yourselves. If you know how to find Jupiter, look through a pair of binoculars or a simple telescope, you'll see these little dots around it, and these dots move. You can watch them orbit around the planet Jupiter over the course of just one evening. They move relatively quickly. So here was evidence that 4 things at least didn't orbit the Earth. These were objects for which the Earth was not the center. And that was a huge discovery, and that overturned our understanding of this geocentric, Earth-centered model into understanding that the universe was a much more complicated place than we thought it was. Here's an up-close view of Jupiter's 4 moons taken by a spacecraft orbiting Jupiter. These are Io, Europa, Ganymede, and Callisto. Much more detailed view of what Galileo saw through his little homemade telescope 400 years ago. And now we understand where the universe came from. We understand that the universe began about 13.8 billion years ago in an event called the Big Bang. Now, we don't have enough time to go into the Big Bang in detail and understand exactly why we think this is the case, but all the evidence we have from looking at the universe tells us the universe is 13.8 billion years old. It started in an event. We don't know how that event started, what caused it, but something happened 13.8 billion years ago, and that created the universe. Not just all the stuff in the universe, but it created space and time as well. People often ask me, what was there before the Big Bang? And whereas that's a perfectly grammatically sensible question to ask, it doesn't make any sense in science. There wasn't a before the Big Bang because time didn't exist. You can't have a before if time didn't exist. And you can't ask what was there because space didn't exist. There was no space for there to be a there. It all gets very complicated and quite muddled. But this is our current state-of-the-art understanding of the universe, that it began in a Big Bang and has evolved to look like it does today. There are many great assets and resources out there you can explore to find out more about space. There are websites like the European Space Agency website, esa.int. You can Google all the spacecraft that are up there. The Mars Curiosity rover is one of the robot spacecraft on the surface of Mars. So just doing a simple Google search for Mars robots will find you this. You might have noticed in the news recently that private space companies are now flying astronauts into space. This is the Crew Dragon spacecraft that just returned to Earth yesterday with 2 astronauts aboard it, splashed down successfully after they spent a few months up aboard the International Space Station. You can spot the space station yourself. You can see an object, an artificial satellite orbiting around the Earth. It's permanently crewed by usually 3 or 6 people at one time. You can see it passing overhead. It's a super bright object visible in the night sky. Go to Spot the Station website. That'll tell you exactly where and when to look, and make sure you give a wave to the astronauts up there. Who knows, they might be looking back at you as you're looking up at them. There are amazing things to see in the sky. This month, in August, is a spectacular month for a meteor shower. There's a meteor shower called the Perseids that happens overnight on the 12th and the 13th of August every year, where you can see shooting stars. If you've got a good, clear, dark sky, worthwhile heading out somewhere as dark as possible. And we're quite lucky in Scotland because we have some very dark skies indeed. And in those dark skies, we can see thousands of stars. We can see the Milky Way galaxy. We can see shooting stars. Most of us who live in towns and cities don't see a sky like this, but it just takes a little bit of an effort to move out of the cities, out somewhere dark. This is a light pollution map of Europe, showing where all the cities are. The bright patches are where light pollution is, where lots of people are living. But you can see in Scotland, there's quite a large part of Scotland that is relatively sparsely populated. It doesn't have that much light pollution, doesn't have that much interference in terms of getting in the way of your view of the night sky. So all of these amazing things we've learned about space can be discovered in school, can be discovered online. Here at the Science Centre, we have an incredible planetarium. Certainly encourage you all to visit once we reopen. In the planetarium, you will be guided by an astronomer like me, talking about the night sky, showing you what stars are visible, what planets are up, but then flying through the universe, flying into the rings of Saturn, for example, outside our galaxy, to the very edges of the known universe. And if you're interested in finding out more about stargazing, if you're looking to take it up as a hobby, or even just get outside and look up and see some of these inspiring sights, there are lots of great resources. There are amazing books like this one. I wrote this one myself. I'd like to give it a little plug. Stargazing for Dummies, but there are lots of other amazing astronomy guides out there, both in printed form and online. And hopefully the things that the pupils will learn in school will inspire them to get into science. Astronomy is such an exciting subject, such an amazing subject that we're learning so much more about the universe every year. And the children in school are being taught this cutting edge science all the time, and they might bring this information home. You might not know where to start, but books like Stargazing for Dummies, visits to the planetarium, just visits to these websites we've talked about are a great place to begin. And I believe I've come to the end of my presentation. So I've been noticing a few chats going up as I've been talking, but I've not been able to see those. I'm going to switch the chat now to have a look at some of those comments and questions. If anyone's got any questions that you want to ask, either about Glasgow Science Centre or about astronomy or about the curriculum for excellence and how it deals with astronomy, anything you want to ask of a captive astronomer, now's your chance. But let me stop sharing my screen and go back to have a look at the chats. So stick your questions in there and let's see what we've got. Well, a few questions in already. Excellent. A question that was asked at 10:30. Was there ever a planet before Mercury? So in terms of when the planets all formed at the same time, about 4.6 billion years ago. We know that we can measure the age of planets from a few different routes. So we know the solar system is roughly 4.6 billion years old. And when the solar system first formed, there were many more than just 8 planets in it. We've got 8 planets now: Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune. Pluto isn't a planet anymore. And if you want to know, you can ask in chat and I'll tell you why that is. But in the early days of the solar system, the first few million years of the solar system, it was a much more violent place than it is now. There were perhaps hundreds of what we call protoplanets, early planets that were swirling around the sun, smashing into each other, breaking apart and reforming, till eventually the solar system calmed down and settled into the form it has today. And the form it has today is roughly the form it's always had, with Mercury closest to the sun and Neptune furthest from the sun. So there certainly could have been a time before the planet settled down that there was an early planet, a protoplanet orbiting closer to the sun than Mercury. There's nothing to prevent that physically happening. It's just in our solar system, Mercury is the closest one that there is to the sun. There certainly aren't any hidden planets out there that we haven't discovered. We understand our solar system well. We can study it both with spacecraft, with telescopes, and with mathematics. Our mathematics tells us we've found all the big things in the solar system. There's nothing hiding that would come upon us unexpectedly. But yeah, there might have been a planet there billions of years ago before things settled down a little bit. And then Francie asked, what was this planet? Was it Saturn? If that was in reference to the picture of Enceladus. Enceladus, yes, the moon of Saturn. So that is one of the 80 plus moons that orbit the ring planet Saturn. It's by no means the biggest one, but it's one of the most interesting moons of Saturn, because it's one of the few places that we know for a fact have got saltwater oceans. And then Snehi asked, does space keep growing bigger? If so, how fast? That's a really good question. So space, the universe is expanding. The Big Bang happened 13.8 billion years ago. And ever since then, the universe has been expanding and getting bigger and bigger and bigger. Now, it's hard to visualize it, so don't worry if you can't visualize what I'm about to say. But it's not like an empty box with something exploding inside it, because remember, space didn't exist before the explosion happened, before the Big Bang. So there isn't space that the universe is expanding into. Space itself is what's expanding. It's not that things are hurtling through space because of the explosion. Space itself is expanding. And imagine it, if you picture the universe like a balloon. It's not that helpful, but it might help in this instance. If you have a balloon, you blow it up halfway, don't tie it off yet, just blow it up halfway, then draw little galaxies on it with a marker pen, and then begin to inflate the balloon some more. You'll notice that all the galaxies are moving away from each other because the skin of the balloon is stretching. That's what happens. That's what's happening in the universe. The universe is expanding. The space between the galaxies, the skin of the balloon, if you like, is stretching and pushing everything away from everything else. So space is getting bigger. And not only that, really strangely, we just found this out in the past few decades, that the expansion of the universe is getting faster and faster over time. Now, we didn't expect this to happen. It doesn't make any sense. The only way that it makes sense is if there's something that we don't yet understand woven into the fabric of space itself that is pushing space faster than the Big Bang pushed it. We call this thing dark energy, but we don't know if it's dark. We don't know if it's energy. We've just called it that. So we've got a name to call it. But something is certainly making the universe getting faster all the time. And if you look to the very edges of the universe, out into deep space with the most powerful telescopes we have, those galaxies are expanding away from us faster than the speed of light. That doesn't seem to make sense, because Einstein told us that nothing can move through space faster than light. That is true. But he didn't tell us anything about how fast space itself could stretch. And it appears the universe is expanding faster than the speed of light, which is incredible. Then the next question from Francie: what temperature is the great red spot on Jupiter? I don't know. That's a good answer in science. Sometimes I don't know is a useful answer. It provokes curiosity. So if you don't mind, I'm going to Google it. Jupiter is not very hot, so it's not a hot thing. Jupiter is about 5 times further from the sun than the Earth, so it gets about 1/30th of the sun's energy that we get. So Jupiter is a cold place. But if I Google how hot is the Great Red Spot, it will hopefully tell us. I was just going to guess, but I won't embarrass myself in case I'm drastically wrong. Oh, turns out I'm wrong. Here we go. Every day's a school day. So according to National Geographic, the Great Red Spot, incidentally, is a giant storm on Jupiter. It's about 3 times bigger than the planet Earth, so it's a big, big storm. It's been raging for hundreds of years. As long as we've had telescopes to see it, it's been there. And because it's such a vast, non-stop thunderstorm, apparently it heats itself up to about 1,300 degrees Celsius. There you go. I will use that information in future talks. I didn't know that, so thanks for asking the question. So yeah, 1,300 degrees Celsius, but the rest of Jupiter is much colder because Jupiter is very far from the sun, doesn't get too much energy from the sun compared to the Earth. Then we have a question about how we can study space. If it's of interest, it depends what you mean by study. So there are many people who are fascinated by space and interested in studying it and learning about it just from the comfort of their own homes, and you'll learn about it in school. Perhaps you don't want to study it as a job or study it at university or college, but maybe you're interested enough to pick up some great astronomy books or watch some documentaries. And there are many great places you can go for information. So I think my first recommendation would always be, if you've got a planetarium local to you, come and visit a planetarium. They are breathtaking places of learning and give you an amazing sense of the universe. So anyone local to Glasgow can come to our planetarium, but there are planetariums around the country. Ours is the best, but hopefully we'll see you here. Our planetarium, when it reopens, read online. There are magazines you can buy. You can download them online, or you can buy them in shops that will tell you month by month what's up in the sky. You can start your stargazing hobby. Don't rush out and buy a telescope. Start with a good pair of binoculars, even just one you found rattling about in your house. Binoculars are a really good tool for astronomy, help you explore the sky in a lot of detail. They'll teach you one important lesson as well, and that is whether you enjoy standing outside in the winter in the freezing cold at night. If the answer to that question is no, then perhaps stargazing isn't for you, but you can still be interested in astronomy and study it. If you want to study it formally, there are many universities in Scotland that offer astronomy courses. I studied at Glasgow University. It's one of many that offer great astronomy courses, and you can keep going. There are friends of mine who continue studying astronomy to this day. I used to work in the university. I've now moved to working in the Science Centre, and it's my job to talk about astronomy. I don't study the universe anymore. I read what other people have studied of it and communicate that to people. So I'm very lucky to be able to do the job that I do. And then on a happy note, Suzanne asks, will the planet Earth ever die? Yep. I'll expand on that in case you get worried. The planet Earth will eventually die, not because the planet itself will die, but because the sun will. Our sun, like all the stars up there, have a finite fuel source. The fuel source on stars is hydrogen gas for most of their life. They burn hydrogen to make helium, and the sun only has a certain amount of hydrogen. When it runs out of hydrogen, it'll start to die. And it'll begin to burn a bit of helium because it'll panic. It'll start to try and get energy from somewhere else. It'll collapse a little bit under gravity. A star's whole life is a battle between gravity trying to collapse it and the energy it produces pushing it apart. As long as those two forces are balanced, a star can shine. When it runs out of hydrogen, gravity will take over and start to shrink it. But as it shrinks it, it'll get hot enough in the core of the sun that it can start to burn helium. And when it starts to burn helium, helium actually pushes out a bit more than hydrogen does. It will make the star, our sun, expand. And over the course of a few million years, the sun will expand and it will swallow Mercury and Venus and Earth and possibly Mars as well. So at some point in the future, the Earth is going to be inside the sun. That's not good news for anyone, but don't panic because it's not going to happen for billions of years. Our current estimate is a few billion years before the sun swallows the Earth, and that's the point where the Earth will die. And again, our brains don't understand, we haven't evolved to understand huge timescales like that. It might make you more worried than it should, but don't panic. The sun expanding is nothing we have to worry about. It does remind me of a story that I heard, probably not a true story, about a lecturer who was telling that fact to an audience, and someone looked rather worried and put their hand up and said, "Excuse me, did you say it was going to swallow the Earth in a few billion years?" And the lecturer said, "Yes, a few billion." And the person said, "Oh, thank goodness. I thought you said a few million." as if that will make any difference at all. It's going to be a long time in the future before we have to worry about anything like that. And then we have another question from Snehi about planets colliding. Well, are there any planets colliding with each other? So not in our solar system. Our solar system has fairly stable orbits of the planets. All the major planets are in stable orbits, and the moons orbiting those planets are fixed and stable. What can happen is little bits of debris in space, the leftovers of when the planets were born, little bits of debris can occasionally hit another planet. We call those bits of debris asteroids or meteoroids or comets. And that happens on all the planets, and it happens on Earth. When it happens on Earth, if it's a small piece of debris, it'll burn up in the atmosphere and causing a beautiful shooting star to streak across the sky. That's when we see these meteor showers that I was talking about, the Perseids meteor shower coming up in a few days' time. If something very big hit the Earth, it could cause problems. If it's big enough to not burn up and land on the surface of the Earth, it could cause problems. It could cause craters. It could damage towns and cities. Nothing like that has happened yet, but it will eventually happen given enough time. But I suppose it's one of the reasons why astronomy is not only an interesting subject, but an important subject. The more we understand about the universe, the more we can detect these bits of debris in space, the more time we'll have to plan what to do if we find a comet hurtling our direction. Whether we send Bruce Willis up with some explosives to blow it up, probably not a good idea. But the longer we have to do something about it, the more likely we will be able to save the world if anything like that was to happen. Again, it's unlikely to happen in our lifetimes, but it is just a matter of when it will happen, when the Earth will get hit by a very big thing. The last really big thing to hit the Earth was 65 million years ago. That wiped out the dinosaurs. So who knows what will happen in the distant future. In terms of other planets elsewhere colliding, certainly that will happen. In the early solar system, planets smashed into each other all the time. So the busier your part of space is, the more things in it, the more likely it is that they will collide with each other. I'm sure there are planets out there, as I speak, that are colliding with each other because space is big. There's lots of stars, lots of planets, lots of places that these collisions can happen. Wow, these have been fantastic questions. Thank you all so much for them. I think we've come to the end. It is just a couple of minutes before 11 o'clock in the morning. As it was mentioned at the start in the introduction, if anyone has got other questions, feel free to fire them into the Zoom chat. At the end, we might, if there are questions that can be forwarded on to me, I might send the answers back to the National Parenting Forum. They can send the answers on. But I'd like to thank you all so much for joining us this morning. And I will hand back to my colleagues at National Parenting Forum, and apparently they're going to disconnect me, and I'll stop appearing on your screens. Goodbye.